In the last video, we figured out how to find a basis for the null space of a matrix A. And that null space consisted of the fundamental solutions to the matrix equation Ax equals 0, which you could find by putting A into row-reduced echelon form. The other subspace associated to a matrix A is its column space, and in this video we're going to look at the problem of finding a basis for the column space of a matrix. Now, one comment is that this actually solves a more general problem. So if you gave me any sequence of column vectors of the same height and asked what was the dimension of the span of those vectors, well, I could now just put those vectors, make those vectors the columns of a matrix, and then do what we're going to do in this video, so it would solve that more general problem as well. To do this, interestingly enough, we need to introduce the idea of the row space of a matrix, and you'll see why that is in a moment. So the row space of an m by n matrix A is defined to be what you think it should be, the span of the rows of A. So for example, if your matrix A was 1, 2, 3, 4, then the row space will be the subspace of the space of all 1 by 2 row vectors spanned by the 1 by 2 row vector 1, 2, that's the first row of A, and the second row of A, 3, 4. Now, the reason we want to introduce row space is because doing row operations changes the column space, but it doesn't change the row space. The way we're going to see this is we're going to use the fact that we know that doing a row operation is the same as left multiplying by an invertible matrix. And I claim that if E is an invertible matrix, then the row space of EA is the same as the row space of A. Let's look at why that's true. Well, one reason is that we know that the rows of EA are linear combinations of the rows of A. We proved this when we started studying matrix multiplication, and we looked at it from a column point of view and from a row point of view. And specifically, this result is follows immediately from 3.2.6. Okay, the rows of EA are linear combinations of the rows of A, so elements of the row space of A. Now, the row space of A is a subspace. It's the span of something, and spans are always subspaces. So the subspace spanned by the rows of EA will, again, be a subspace of the row space of A. So let's say row space of EA is going to be a subset, in fact a subspace, of course, of the row space of A. Okay, but now we can just play the same game again. So just doing exactly the same thing with e to the minus 1 in place of E, and with EA in place of A. What would that give us? That will give us that the row space of E to the minus 1 times EA is a subspace of the row space of EA. Right, what you've got there is A. So we've seen that the row space of EA is a subspace of the row space of A, and the row space of A is a subspace of the row space of EA, so they're equal. Okay, so multiplying on the left by an invertible matrix doesn't change the row space, and in particular, doing row operations doesn't change the row space. So let's make this comment. The reason that this is useful is because we can do row operations to a matrix A until we reach a row-reduced echelon form matrix, and in fact it's very easy to find a basis for the row space of a row-reduced echelon form matrix. We'll see how to do this in a second. So you might think, haven't we solved the wrong problem here? I mean, we were supposed to be interested in the column space, and I've ended up finding a useful way to find a basis for the row space. Well, of course, we can just swap rows and columns. So just to get around this, we can simply transpose all our matrices so that the row space becomes the column space and the column space becomes the row space. So let's look at why it is easy to find a basis for the row space of a row-reduced echelon form matrix. So what I claim in this theorem is that if you've got m by n row-reduced echelon form matrix, then the non-zero rows of that matrix are actually a basis for the row space. So proof. This is just like the easy linear independence criterion which we met before. So let the non-zero rows of R be, let's say, C1 up to C was a bad choice. Let's say R1 up to R L. Now, each of these non-zero rows must contain a leading entry. So let's look at where the leading entry appears. We'll say that Ci is the number of the column in which the row I leading entry appears. So just to keep track of what's going on, let's look at this in an example down here. Here we have L is equal to 2. There are two non-zero rows, and row 1 has its leading entry in column 2. So C1 will be equal to 2, and row 2 has its leading entry just here in column 4, so C2 will be equal to 4. And now let's recall part of the definition of the row-reduced echelon form, which is that if a column contains a leading entry, every other entry in that column must be 0. So here these entries are 0, and here these entries are 0. So let's now suppose that we've got a linear dependence on these rows. So what if we had sum from I equals 1 to L of AI times Ri equal to the 0 vector? Well, what happens if we consider the entry in position Ci on the left-hand side? So let's fix some number. So fix some j between 1 and L. So the entry in column J of that linear combination is, well, I claim it's AJ because, first of all, row J has a 1 as its leading entry, so it's got a 1 in column CJ. Remember, in a row-reduced echelon form matrix, all leading entries must be 1. And also, all other entries in that column must be 0. So Rj prime for j prime not equal to j are 0 in column J, column Cj. Okay, that shouldn't have been underlined. Okay, so what have we got then? Let's just separate this off. So what's happening? I've got AJ on the left equals 0 on the right. Okay, for any j, we've shown that the coefficient AJ must be 0, and therefore these things are linearly independent. So just to return to our example, if you're not quite sure what was going on in that proof, just look at what would happen in this example here. If we had A1 times 0, 1, 2, 0, 3 plus A2 times 0, 0, 0, 1, 4, well, that would be, so 0, A1, and then a bunch of stuff, more stuff, and then in position 4, we just get A2. Right, so if this was equal to the 0 vector, then just looking at position 2, looking at the column C1, so that's column 2, you can see that A1 has to be 0. And if you look at column 4, so the column C2, which was 4, then that's just going to be A2, so A2 has to be equal to 0 as well. So now we're ready to have to write down our procedure for finding a basis for the column space of a matrix A. So what we'll do is just swap columns into rows by taking the transpose. So the procedure is as follows. You put the transpose of A transpose, into row reduced echelon form by doing row operations, and then the non-zero rows of that row reduced echelon form matrix, as we've just seen, are a basis of the row space of the transpose. But because transpose swaps rows and columns, the transpose of these non-zero rows will be a basis for the column space of A. So let's do an example. We're going to take A to be my favorite 3 by 3 matrix. There it goes. So the first thing is to put A transpose into row reduced echelon form. So A transpose goes 1, 4, 7, 2, 5, 8, 3, 6, 9, like this. So we've swapped columns and rows. The first row of A transpose is the first column of A, and so on. So if you do row operations, then the row reduced echelon form matrix that you reach is 1, 0, minus 1, 0, 1, 2, 0, 0, 0. So there are 2 non-zero rows. So the dimension of the column space of A is 2, and a basis for C of A, the column space of A, is the transpose of those 2 non-zero rows. So 1, 0, minus 1, that's the transpose of the first row, and 0, 1, 2, which is the transpose of the second row.